I welcome you now to Lecture 4A, entitled Partial Derivatives. And this material comes from section 15.3 of the textbook. The objectives of this module is to know how to compute the partial derivatives of a multivariable function. And the concepts that we'll develop are, in fact, what we mean by partial derivatives, and also the distinction between a partial derivative and a direct derivative. So as usual, the second slide is just an outline of the slides to follow. I'll just move from here on to the main body of this lecture. So let's look at the issue of partial derivatives and why are they necessary. And the motivation is basically develop the tools that allow us to determine the slope that an individual sees when walking a path, for instance, along a mountainside. We'll actually solve this problem in Lecture 6 once we basically establish the tools that are required. If you look at the picture on the right, this shows you, for instance, a hiker that's sort of in a saddle, and the hiker has a choice of walking down the hill or walking east or walking west or north. And so the hiker wants to know that in the path in which he or she is walking, at any given point on the hill, what is the slope at that point? So the slope now depends on direction traversed. So how do you go about basically determining what the slope is? So if you look on the left, there's a mathematical description, the same picture. So you have a specific point at the top, which in this case is the origin, and the hiker is at a certain elevation, which would be the function f evaluated at 0, 0. And so we have different paths that we can take going down the hill. And the question is, how are we supposed to determine what the slope is in a particular direction? So at this point, we need to define something. And again, definitions are an act of creation. We do it because it might turn out to be useful, and of course it is useful. But now the problem is that we have some degrees of freedom which we did not have when we dealt with single variable. In the single variable case, we could only move along the x-axis, so either forward or backwards. So there was one derivative. So given that there was only a single derivative, we called that a direct derivative, right? Now, on the other hand, we can go in the x or y direction, or we can go in any arbitrary direction in the xy plane. And in the process, we're walking down the hill, which means the value of z is changing as we change the values of x and y. So in this case, we now have two possible things to consider. And that is, what happens if we move in the x direction? And what happens if we move in the y direction? Not only that, when we move in the x direction, we can already be establishing a particular value of y at which we're moving in the x direction. Or correspondingly, if we want to determine how the slope changes with y, we could be establishing a certain value of x. We're determining the slope in the y direction. So we use the same definitions for derivatives as we did in first year. The only difference being that when we take the partial derivative with respect to x, we're keeping y constant and only varying x. We're taking derivative with respect to y, we're basically keeping x constant and varying y. So you can see in the case of the partial derivative f subscript x, we're taking the difference between x evaluated at a plus h and x evaluated at a, and dividing by the difference, which is h, holding the x component, the y component constant at a value b. In the case of the f partial y, then we basically are dealing with evaluating y at b plus h and at b, keeping the x value constant at a, taking the difference and dividing by h. And in both cases, if we take the limit as h approaches 0, we're defining the partial derivative. So f partial x or f partial y. So what we're doing effectively is take the partial derivative with respect to x holding y constant, or take the partial derivative with respect to y holding x constant. All right, so here's a picture of how we can visualize the partial derivative of f with respect to x. So you have a particular hill, which is the top left hand. And then what we're doing basically is we're going to hold the value of y constant at a certain value of b, but x can move. So we're tracing out a line. Okay, that line is the one shown in black on the right, which is here. Okay, so that's the curve. And that's basically at some point. All right, so now what we're going to do in the bottom left-hand corner, we're going to take 2 points, one at A and one at A plus H. And of course, B is held constant. And then we're going to basically compute the slope between those two lines. So this is a straight line that you see here. And then what we do is we let H go to 0, which means this point is slowly but surely moving towards this point. And in the limit, we're dealing with a line which is tangent to the point on this surface at this point, but in the x direction, evaluate at the point x, y equals AB. So that's how you can visualize what the partial derivative is with respect to x. Now you can also visualize this. There's a little interactive module that you can click on, and you can play with basically what those lines look like. And then in the limit, you get the tangent slope. You can choose different A's and different B's just to watch what happens with these slopes for the two different lines. One would be this one here, and then as H goes to 0, then this would approach the line that you see here. All right, now let's do f partial y. In this case, basically, x is held constant. So in this case, x is equal to a. And now basically, we're basically tracing out y. And that's the curve that you see here. And we're interested at the point AB again. And so the function takes on the value of f of AB at this location here. That's in the vertical direction. All right, so next thing we want to do is basically take 2 points, one at B plus H. And then the difference divided by H basically turns out to be just the line that we're looking at here. And then if we let H goes to 0, which means this line's moving in this direction, then we approach this line, which is the tangent at this location here. And so more or less, we've just extended the notion of a derivative now to more than one variable, but we need 2 derivatives now, and we call them partial. And by the way, partial is always given this squiggly D sign here. All right, so just keep that in mind. If it's a direct derivative, it'll be a standard D value. All right, and this again is an interactive figure where now we're looking at the partial derivative with respect to f with respect to y. And so this would be, for instance, the line that you would see if h is some small value. And as h approaches 0, then this line basically finally becomes the tangent line, tangent to the point on the surface here, defined as AB, f at AB. All right, what about the calculation of partial derivatives? Well, there are 2 approaches to take. One is using the standard definition. You're given a function here, for instance, fxy equals x squared plus y, x squared times y. And we want to compute df dx and df dy. So if we do df dx, then we would basically hold y constant. And so in this case, y just is something. And this becomes x plus h, and this becomes x. The difference between those divided by h. Make the substitution of x plus h into here. And y. Do this computation. And finally, you end up with the limit of h approaching 0 of this expression. But h's cancel out, and you're left with 2xy. You can do the same thing with partial with respect to y. In this case, you hold x constant. This is y valued at y plus h. This is the original y. You take the difference between the two, divide by h. Take the limit as h approaches 0. So in this case, y plus h gets substituted in here. And we end up with an expression that looks like this, as h basically goes to 0. All right, so now in the limit, basically, this expression here will just become x squared. The y and minus y will cancel, right? And you just have x squared h over h cancels, and you have x squared. All right, this may be necessary in some cases to do. but in most cases, if you're dealing with perfectly analytical functions, then we can basically calculate partial derivatives by treating the one of the variables as a constant. So just use all the rules that you applied last year when you're taking derivatives. So for instance, if you're taking the partial with respect to x, then y is treated as a constant, which means it can come outside. And so you're only taking the derivative of x squared with respect to x, and you end up with 2xy, which is the same as here. For f partial y, basically, in this case, you're holding x constant, so x can come outside. If you take derivative with respect to y, that's 1, so you get x squared. And now, in this particular example, they're asking you to evaluate what those partials are at the point 1 and 2. So you would substitute 1 and 2 here, and there's no y, so you just substitute 1 here, and you end up with the resultant answers that the partial f with respect to x is 4, partial f with respect to y is 1. This was computed holding y constant. This was computed holding x constant. Okay, so let's take another example, 3 here. Let's compute the partial derivatives using the product rule. So compute dgx and dgy. So if you take dgx, you take basically derivative of this with respect to x times this, and then the derivative of this with respect to x times this. For y would be take derivative of just this term with respect to y, because this is just appears as a constant. So this is really all that's happened here. You've got the first, we take derivative with respect to this, and then take derivative with respect to the x squared term. So you work this out, and you'll end up with an expression that looks like this. With derivative with respect to y, partial, the x squared can come out, and so you're just taking the derivative of this expression, and you end up with x cubed e to the power xy. Again, this is with x held constant, this was with y held constant. All right, well, if you can take a partial derivative, why not take higher order partial derivatives? For a single variable case, there was only x to consider, so you could take the first derivative, the second derivative, the third derivative. But here, you have different options now, because you can take the partial with respect to x or y in various combinations. And so the simple little formula that I've shown here, m is the number of variables, and n is the order of the partial derivatives. So first order would be n equals 1, right? N equals 1, m is number of variables, 2. So there were only 2 partial derivatives, f partial x, f partial y. Let's say we're interested in second order, which means we'll take a second order derivative. Then this becomes 2, m is 2. That means there are 4 possible combinations of second order partial derivatives. And so I've listed them here. You can also go to higher orders. If n equals 3, then you can see how this will scale in terms of the number of partials that you have to derive. So here's 1. This is derivative with respect to x twice. This is derivative with respect to y twice. This is derivative with respect to y followed by x, and this is derivative with respect to x followed by y. All right, so there are different ways of writing it. This is one form of notation. This is another form of notation that you see here. And this is more or less putting things in words in terms of how these things are described. So this is more or less what we mean by taking higher order partial derivatives and the notation. Now, why is this important? Well, when we start looking at approximating surfaces, we will use a Taylor expansion. Now, if you use a Taylor expansion, you make use of higher order partial derivatives. So that's more or less the motivation. You'll also need this, for instance, if you want to determine critical points. In other words, is there a local max or a local min? You will need this information for that. All right, so let's take an example of computing second partial derivatives for the function as given. So if you take df by dx, right, you get basically the expression that you see here at the end. And f partial y, you get the expression that you see here. So again, here we're using basically a combination of product rule and just summation terms. Anyway, you can work through these examples to prove to yourself that these results are correct. All right, now we have to take the second order partial. So we have basically the f partial x, which was this one, and f partial y, which is this one, which was computed on the previous page. So here we're going to take the derivative of this one with respect to x, which will be taking it twice. Here we're taking y twice. Here we're taking the original of y and now taking derivative with respect to x. Here we were starting with the original for x, partial for x, and taking derivative with respect to y. So if you look at this, you end up with second derivatives looking like this. And now these two are curious because what you'll end up with is this looking like this. And lo and behold, this is identical. So the order in which you differentiate does not seem to make a difference. Your answer is always the same. The question is this always the case? Well, the next theorem will answer this question, and that's called the Clairol equality of mixed partial derivatives. We assume f is defined in an open set D of R2, and that fx partial xy and f partial yx are continuous throughout D. Then, only then, f partial xy equals f partial yx at all points of D. Assuming sufficient continuity, theorem 15.4 can be extended to higher derivatives f. For example, fxyx equals fxxy equals fyxx. Right? In this case, you would have to show that all of those three partial derivatives, are basically continuous. Right? That's basically how you would go about doing it. We know how to prove continuity, and so you have the tools that allow you to do that. All right, so that concludes Lecture 4A. We'll be discussing more on this subject in Lecture 4B. Anyways, thank you very much for listening.